Okay, so today I'm going to be reviewing this 2007 paper on making good user interfaces for mobile robots. So let's take a look at this user interface and try and figure out what's kind of going on in the environment of the robot. So we can see that the camera feed shows a hallway, and then we can look on the left. We have this laser feed, and we can see there's um, the hallway in front of the laser, and there's a bit of noise in that laser, but it looks like we can see that hallway leading in front of the robot. Okay, then we can look at the sonar, and it's not really clear what that's showing. Um, and then we can move over to the map, and again, it's not really clear where we are on the map. And but then we could look at the compass and say, okay, we are slightly west of south, and so if we move around the robot a little bit, we can kind of get a sense of how the map is oriented, and we might be able to start to figure out um, where we're on the map and kind of consolidate all the information together. But it seems like we had to do a lot of work to get that to kind of put all the pieces of information together. And so there should be a way to make that a little bit easier to make a better interface. And so let's look at some of the things we could do. So one of the solutions that has been explored is adding more robot autonomy. So instead of making a better user interface, we just add some autonomy. Maybe we say the robot can um, avoid obstacles on its own. Maybe we add features like it'll automatically open doors as you're exploring, and things like that. But the problem is that it doesn't tackle the root problem of not having the best interface that you can. And you're only going to be able to program so much autonomy into the robot. There's going to be things that the human has to kind of intervene in and kind of direct the robot to do. And for that, we need a good user interface. So another solution is to add more interaction methods, like maybe haptic feedback or giving the user some like surround sound of the environment. And um, this is pretty good. It's a way to get more information to the user, but the problem is that if the user is kind of already bombarded with too much information, just adding more in kind of and not if you just kind of add more information, throw more information at them, they're not necessarily going to be able to use it. And so that's where the idea of trying to present this information in a more easily accessible form becomes important. And so we can look at that third bullet point. How can we improve the situational awareness of the user so they kind of get a better sense of their surroundings in an easier way? And so one solution is to add more cameras. So if we have like a panoramic view around the robot, then you can kind of look around in the environment and get a sense of where you are in 3D space and control the robot accordingly. So the only problem with that is that sometimes you don't always have that kind of bandwidth to stream that many cameras, and um, and doing that you might create a lot of lag, and lag can create its own problems for teleoperation. But if you do get that to work, then that definitely would be a nice solution. Um, so another solution would be to use VR, and um, so this is a pretty good solution because it gives the user a good sense of the environment. But again, it might not be applicable in all scenarios. And so in this paper, they focused on the case when you'd have just one camera and you have several different sensors, and you're thinking, how do I correlate this data together and make a nice user interface? So the authors of the paper came up with the interface you see on the right, based on kind of two main principles. The first was that useful data is more important than accurate data. So on the left, we can see that there's a lot of data there, and it looks like yeah, you're getting really good data from the laser and the sonar, but it's not really clear what you're supposed to do with that, and it's not really necessarily going to help you control the robot. And so that's where on the right, the interface does a lot better because maybe some of that data isn't as accurate. Maybe we can't see all the noise in that laser, and but the information we do see is it really tells us kind of what are we supposed to be doing in this environment. We can see how close the robot is to obstacles because we have a nice perspective like above and behind the robot, and we can kind of make sure that we avoid the obstacles, and we can also see the video feed projected in front of the robot, and we can kind of correlate those two pieces of information together, and it's a really nice interface. And yeah, this is also where the second principle comes in, where 3D information is more useful than like the 2D representations of that information. And so while like having a 2D map is something that we've seen a lot, it's kind of not the natural way that we perceive the world. We see the world in 3D, so the idea is that the best way to present information to a user is in that 3D form, and that way they can easily just kind of take in that information and act on it rather than having to like transform that information in some way. And so now we're going to look at a couple different experiments that the authors of the paper did to test out their 3D user interface against kind of the more traditional 2D interface. So the first experiment that we're going to look at is a robot control experiment where users had to control a robot through a maze, through like several set waypoints. And so yeah, some of these trials were done like in a simulated environment, and some of them were done in a real environment. And overall, they found that within 3D interface, users were 15% faster at completing the task. They had 87% fewer collisions, and they reported a significantly lower workload compared to the users using the 2D interface, as measured by the NASA TLX. And so yeah, this is pretty good evidence that the 3D interface is working, and users are able to complete better able to complete tasks more efficiently. And since they're able to kind of look around the robot, they can make sure that they're avoiding collisions. Whereas in the 2D interface, it's kind of like they have to move their attention around the screen. They're not able to put all the information together as well, and also the collisions, like they could get focused on one screen. They might be looking at they might get all the information sucked into the video feed, and they might not notice that, oh, the laser feed is showing that they're about to crash into a wall. They don't notice that, and they have a collision. The 3D interface does a lot better job of having all that information in one place and easier to access. So now, looking at experiment 2, we have this is a task kind of in more of an open room rather than a maze with kind of walls and obstacles in the middle. And the 2D interface, we can see that it had a video, and then it had a map that was kind of always oriented with the north facing upward. And then on the 3D interface, we have a camera that's following kind of above and behind the robot. And then we can see the video feed and projected in front of the robot. And again, we see that the 3D interface performed a lot better, where users completing the task 34% faster with 66% fewer collisions. And in this case, the task was kind of to just go around and map out the layout of the whole room. And so, yeah, so this is a slightly different task, and again, the 3D interface is performing better. And so then I'm going to skip over experiment 3 because it doesn't show too much more information than that isn't covered in the other experiments. So looking at experiment 4, this was an experiment designed to measure how the 3D interface performed in the face of delay. And we can see that indeed the 3D interface is still better. Users are able to complete the task faster, and they're still able to cut down on the number of the collisions they do versus the 2D user interface. But one of the interesting things we can notice, if we look at the percent change column of the table on the right, the number of collisions went from being 84% less when there is no collisions in the 3D interface versus the 2D interface, to their 3D interface only being 27% faster. And 27% fewer collisions. And this seems to suggest that as the delay increases, it kind of has a large negative impact on the performance of the users. And so this means that it kind of washes out the positive effect of the 3D interface, and it's just like this delay is just really bad, and it's just making the participants perform badly. But the 3D interface is still a little bit better in those cases. And so now we can look at experiment 5, which is kind of users had to navigate around and control. They use the camera to look down, kind of, so they could control the camera to look kind of sideways to the way that they're moving. And so this is important because they were going down this hallway, and then they had to kind of search down kind of side passages. And so, without the, this experiment was repeated once with a stationary camera just pointing forward, and then one time with a controllable camera we can control it and look sideways as you're driving forward, and you don't have to go into that side hallway. And so this is kind of testing, is the 3D interface helping you maintain that situational awareness of what's happening with the robot as you change the point of view of the camera. And again, we see that the 3D interface is indeed performing better than that 2D interface. But the important thing is that we can see that the 2D interface actually, it didn't really matter if they used the stationary or the controllable camera, because using that controllable camera, it would cost them a lot of time to move it sideways, and so they kind of lost out on all the savings that controllable camera gave them. Whereas in the 3D interface, that controllable camera did actually end up saving them time, because they could kind of turn the camera sideways and continue driving the robot forward, and they had a good sense of what was happening, and they could save time that way. And so now we're going to look at experiment 6, which was kind of an environment search task. Um, participants had to control the robot around an environment and control the camera to look kind of up and down and look at people in the cells, and then kind of provide some information about the people in the cells. And they're given 6 minutes to identify as many people as possible, and they kind of did one of these experiments in the simulation environment, and then they did another kind of similar task in the real world. And they found that again the 3D interface did a lot better in the simulation, but they didn't really find the 3D interface doing any better in the real world. And the way the paper explains this is that the novice users were kind of struggling to control the camera. It was kind of complicated. There's a zoom feature, and so it seemed like it was more about how well could the user control the camera rather than which interface was better than the other. So I guess it's important to keep in mind that um, you know there are a lot of factors in these experiments, and it would be interesting to see if maybe they repeated this experiment, but they had more experienced users that had a lot more time to practice, and they could eliminate that factor. Maybe we could see some different results in this experiment. So now let's go back to our teleoperation interface design principles. What can we learn from this paper? The first is that it's really important to put all of the information in a natural 3D form, and this kind of helps the user figure out what's going on in the environment in a really natural way. And also putting the viewpoint above and behind the robot is very useful, because then you can see the robot and you can kind of see the obstacles around the robot. And then another thing that's important to do is minimizing the rotations and perspective shifts that are required by the user. And so kind of in the 2D interface, you can say that you have a map in one orientation, you have the video feed in another, and maybe you have some sensor data that's in a different orientation, and you have to kind of combine all that information, and it can be really difficult. And so that's where the 3D interface is better, in that all of these rotations are done by the interface itself, and so the user doesn't have to do them. And so then the next design principle is to strive for intuitive controls. And so what can happen in the 2D interface is that you have a video feed showing a camera that's pointed sideways with respect to the robot, and then intuitively when you see a video feed you think forward means going like into the video, but if your camera is not pointed straight forward, then that's not the case. The 3D interface fixes this, because if the camera is pointed sideways, then the video feed will show sideways, but the interface will still show kind of forward as being the direction you go when you go forward. And then there's a similar problem where if you have a map that's pointed north upward, and then you press forward on your joystick, you'd expect the simplest expectation is for the robot to go up the screen, but if your map is showing north, then that's not necessarily the case. And again, the 3D interface fixes this by saying, by being held above and behind the robot, and so when the robot turns, then the direction that you're pointing turns, so that forward means forward. So this is very helpful for making the controls intuitive. So another thing that the paper suggests doing with an interface is to allow for an adjustable perspective, and this is because sometimes it might be good to have that view above and behind the robot. Sometimes maybe you need to get a little bit, zoom out a little bit so you can see a little bit more of your surroundings, so you can plan kind of a longer, make a longer term plan for your robot. And maybe you need to zoom out and see your whole map and kind of plan out some larger scale tasks. So that's where it's really nice to have adjustable perspective so you can have the right thing for what you're trying to do at the moment. However, whenever you're doing those perspective shifts, it's important to maintain situational awareness, which is basically you don't want to just kind of quickly, when you press a button, just jump to a different view, because then the user has to reorient themselves, and that can cost a lot of time. So you want to have more smooth transitions from one viewpoint to another one, so the user can retain the situational awareness that they had from one perspective, and then be like, okay, I know where I am in relation to my old perspective, and I can just continue doing my tasks. And so now looking at some future work, it would be nice, so all of these experiments were done with completely novice users. Maybe they had experience playing video games and things, but they didn't really get time to train with the particular user interface. So it'd be interesting to see if maybe in some cases the 2D interface is actually better, but only when you have the user gets a lot of time to practice with it, because the 3D interface might be better in like more natural and quick to pick up, but the 2D interface might present the data in a more streamlined way. And so that would be a good thing to test with more experienced users. Another thing to do is to refine the 3D interface. So we can kind of see on that picture on the right, there are corners of, we can see all these corners of the walls, and they're supposed to match up with kind of the blue lines on the map, but they don't quite match up because of kind of this kind of how we're oriented with respect to that video. So it'd be interesting to see if there's a way to kind of remove that effect, maybe changing how that image is displayed to make it a little bit better, and so make it that so the user has to do even less work with putting those two pieces of information together. Another interesting example of future work that the paper points out is outdoor terrain. So all of the examples in this paper were completely flat, and kind of they weren't really, and the surfaces were like flat, and they didn't have any like debris on them or anything. So if you're going on a outdoor trail, then you might have an incline, you might have like stones. So it'd be an interesting challenge to say, what information do you include in the interface? What information do you not include? Do you keep the interface do you keep the perspective level, or do you try and tilt it with the tilt of the terrain? And then a fourth thing that could be good for future work is having multiple robots. So yeah, this raises interesting questions of, do you have the video going from multiple robots at the same time? How do you switch between the robots? And things like that. And that also raises the question of what if you had a different role? Instead of controlling a single robot, what if you were more of a supervisor for a robot? Would you need a different interface? How do you toggle between different views while maintaining situational awareness? And so yeah, there's a lot of interesting extensions to this work, but I think this work presents some good principles to think about for why it might be good to move from a 2D centric, kind of like a 2D user interface to more of a 3D user interface, and some of the things to think about as we design the interfaces for remote robots in the future. And thanks for listening to my presentation.